Hi, I'm Michael Killen. I'm with Maritn Perl. I'm now going to ask him about one of the strangest topics I think exists, relativity, or most difficult to understand. Did I articulate that right?
Yeah. It's the relativity discovered by Einstein. And so he discovered, and it's the one he discovered in 1905, which he later generalized, but the one we're talking about is called special relativity. And even he uses the word relativity. It's kind of a bad word, but we're stuck with it. And the problem with understanding it is that it's not common sense. It's not obvious. And again, he built all of this up using mathematics and trying always to make sure that the velocity of light would always be the same, no matter what system and how he measured it.
So a few minutes ago, we focused on E equals mc squared, which doesn't necessarily have anything to do with relativity, does it?
That's right.
And now it's the cornerstone, but correct me, cornerstone of relativity.
Yeah, we're focusing on the C, which is
okay.
Okay. Now here is the great mystery, which there is no way to understand except to accept it, and then if you want to know more, learn the mathematics. You're sitting in your car, or you're sitting in your house, say, and you have a clock, and it goes tick, 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 tick. Somebody takes that same clock and puts it into a car and moves along, and you're able, say with a telescope, to look at the clock ticking the same. And you see tick, tick, tick. But this is a supercar, which goes tremendously fast, very close to the speed of light. And then what you see is tick, tick, tick. The clock goes slower. Now, to the person sitting in the car, it's going tick, tick, tick. But to you, watching this clock in this car going very close to the speed of light, it's going slower. Tick, tick, tick. And it's one of the great, I wouldn't call it a mystery, but that's the way the world works.
All right.
And it's led to a lot of confusion, but it's right.
So let me ask this. If I look out at the universe, and I'm here on Earth, and the clock is ticking here, way far away, somebody traveling in space, they're not using the same basic element of nature, the passing of time, and it's not, you're saying it's not universal.
Depending how fast they, suppose you and they somehow got together and both got a clock, made exactly the same person. What they're doing up there now and what you see depends on what their velocity is relative to your velocity. And there's the word relativity. Everything depends upon one person's velocity relative to the other person's velocity.
It's hard.
It's very hard, because when the velocities are close together, are smaller, 100 miles an hour difference, which is very small, then everything looks the same. But when the velocity, remember we said the velocity of light was 670 million miles per hour. You each take a clock, and somehow this person gets going at 600 million miles per hour. So they're going close to the velocity of light. Their clock, when you look at it, will seem to be going much slower than your clock.
You say seem.
To you.
To me.
To them, it's going at the right speed. There is no way to put that into ordinary life, but it's true.
It's true. So it seems to be two different speeds, two different velocities, right? And one is going almost the speed of light.
Almost 670 million miles an hour.
And time seems to be going slower.
Slower for them, as you see it, through your telescope.
Is that because of the distance?
No.
That I'm looking?
No. Unfortunately, there's no, it's not because of this. They could be passing right by you on a train. There's no way.
There's no explanation
for it. But if you don't allow that, then you don't get, when you work everything out, and we don't have time in this program to do it, you don't get the velocity of light always being c equal to 670 million miles an hour.
Now,
To keep c the same, you must change everything else.
All right, now I'm getting
upset.
So maybe in real life, if somebody was traveling that fast, it appears to us their clock is going slower.
Yeah.
But maybe it's not.
Well, to them it's not, but to us it is. It always is.
Is this to make the mathematics?
To make the mathematics so that when they, whatever they're doing, when they measure the velocity of light and you measure the velocity of light, you always get the same value.
Okay. So
it all hangs on C.
So does this now really reflect the phenomena of the world, or does it reflect the need of physicists, others?
It reflects the way time and space work in the world. It reflects the reality of the world.
All right, I have to take your word for that.
Yeah.
It's not just...
It's not obvious, and there's no way to make it obvious.
It's the way time and space...
When one studies it enough, then you just start using these equations, because if you use the wrong equations, you don't get the right answer. And there are many cases where we do have things moving almost with the velocity of light, namely when we make elementary particles at very high energy. They are moving with the velocity of light. Okay. And then how long they last depends upon how fast they're moving, and if they move fast enough, they will get to us.
They will get to us. Yeah. Okay, so like Einstein tried to put his feet firm on something firm, like the constantness at the speed of light. I do that here. Relativity has to do with two different environments.
Two different environments which are moving at different velocities or speeds. And everything has to do with the relative speed of those two environments.
Two, okay.
If the relative speed is small, then you see every day just the way we see everything on the street. If the relative velocity is large, close to the velocity of light, then everything looks strange.
So, is this where some of those science fiction movies came about? And I don't know if they're science fiction now. If we put somebody on a spaceship and we sent them out, my twin brother, let's say, and 50 years later, he comes back, he's been aging slower than me.
Right, so you're 50 years old, and he's 30 years old.
Would it really be that way?
It will absolutely be that way.
It's amazing.
Yes.
It's amazing.
And that's because he's the one who's gone out and turned around and come back. Because this thing all gets mixed in with force. We haven't discussed force at all, thank God. Because in order to turn him around, you must put force on his rocket ship. And that changes everything. And so that's why he's able to come back younger.
Does that bring us to general relativity?
Doesn't bring us to general relativity. General relativity has to do with the fact that gravity, the force between two objects, is always attractive. And trying to explain that and understanding how that gravity, in our little world, gravity is sort of important, and we have to stand up against it, but otherwise it's a small force. You don't load up your automobile with some kind of gravity or gasoline. It's a small energy, it's a small force. But for the entire universe, gravity is the most important force by far.
Gravity is the most important force.
And that's what he worked on. And then he tried to combine gravity with, which has nothing to do with the speed of light in itself, with electromagnetic theory, namely with electronics, which has to do with the speed of light. So he tried to combine gravity with electromagnetism, and that's called unified theory. And he spent the last 30 or 40 years of his life trying to do that.
And he didn't get there.
Never successfully. And no one has done it since.
Okay. Now, you have some great experience.
A lot of experience, some good, some bad.
Do you think somebody's going to get there in the next 10 years, 20 years?
The biggest problem, and you have to remember I'm an experimental physicist, I do experiments, is that gravity is very hard to work with because it's so simple. I mean, we know one force exerts a certain gravitational force on another force, and you can measure that over and over again. It's always the same thing. We don't know how to get into gravity the way we have gotten into electromagnetism with quantum mechanics. And so that's where all the wonderful things that have to do with electromagnetism have come, the transistor radio and all that. But gravity is, we don't know how to get into it. We don't understand it.
So some of these other forces, or like light, it's waves.
Yeah, that we know how to deal with.
But we can't waves to gravity?
Gravity has waves, but we'll soon be measuring them, but gravity is always in the large. It's always the very big. And most of our technical progress, which has been in electromagnetics, has been in the small things. We don't get to understand those. If I'll now say one thing, which is probably not terribly meaningful, the big problem is that all the other forces, the electromagnetic force and the nuclear force, are amenable to what's called quantum mechanics. No one knows how to apply quantum mechanics properly to gravity because we don't know how to do any quantum mechanical experiments on gravity.
That's interesting.
That's for young people to do.
Yeah. All right, we have 1 minute left, and can you say one significance of relativity?
Well, the great significance of relativity has to do with realizing that there is no one world or one place where everything, you can calculate everything in that place. There's not one world. You can work in any world as long as it's moving along with respect to some other world. So relativity has destroyed our absolute place in the universe. Not everybody agrees, but that's what relativity has done.
All right, you've been wonderful. My guest has been Maritn Perl, 1995 winner of the Nobel Prize, finding the element tau. And we discuss E equals mc squared and relativity. And also during the program, I believe from time to time, pictures of Einstein have flashed on the screen. They are by the great artist Leonard Brager. I'm Michael Killen. Thank you.